All right, everyone, let's then start by going through the weekly exercise in a bit more details, right? This is the PDF. Okay. The weekly exercise number 1 is to implement the original classic DB scan algorithm. How exactly should you do that? Well, the paper that I put up, that you have some sections there that are required reading, there is an algorithm there. Actually, I will open it so we can take a look. There's an algorithm there that you can follow if you want. Here. Here. Pseudocode of original sequential DB scan algorithm. This is one way to do it. The other way to do it would be to simply follow the slides. I will tell you my personal preference. I think that this algorithm here is a bit overcomplicated. My personal implementation is slightly different, and I believe slightly simpler, and I hope correct. Well, at least it is as far as I tested it. So you can use both sources, right? It doesn't matter, as long as the results make sense. If you follow the pseudocode, well, basically you have it almost ready for you. You just have to type it in a certain way that fits your programming language, right? I guess for like Python, for example, this would fit very nicely. So it's up to you, as long as it works. I mean, it makes no sense for me to tell you, oh, you cannot look at the algorithm or anything, because that makes absolutely no sense. So you have the algorithm, you have the slides, and I believe that from the slides, it's also possible to understand, the rough idea of the algorithm and implement it anyway. One thing that you might ask yourself is this thing here, range query. If you look at the algorithm, neighbors n is assigned the results of a range query. This range query is nothing but a neighbor query. It says range query because it's not this the usual nearest neighbors query, because usually when we talk about nearest neighbors, what you do is you ask for a certain amount of nearest neighbors, right? Okay, give me the 10 nearest neighbors, or give me the 20 nearest neighbors, and so on. In this case, that's not what's happening. In this case, they're asking for, give me all the neighbors that are within a certain distance from me, right? So that's why it's called a range query, not like a neighbor query. Although they are neighbors, but the number of neighbors is variable because it depends on a certain threshold of distance, right? And then you see like range query, then DB. DB is basically just, the data set. Distance is the distance function that you're going to use. That's just usually is just Euclidean distance, but it could change. Then P is the actual point where let's say the center of this neighborhood that you're querying. And then epsilon, which is the radius that you actually want. So these are the parameters that you need in order to actually do this range query. And how you do it, like, this is completely abstracted away from the algorithm, right? So they don't tell you like, oh, this is how you do a range query. They just consider like it's a range query. Deal with it, right? In whatever way you can deal it with, in using your programming language or your libraries or whatever. So it doesn't matter. It's just like a concept of a range query. And of course, like we discussed before, there are efficient ways of doing this, and there are raw or crude ways of doing this. Don't worry for efficiency at this point. I mean, of course, if you want to implement this range query very roughly and then get your algorithm working, then maybe as a second step, as like, okay, it's working, I'm safe. Then as a second step, you might think, oh, okay, maybe I'll try to optimize this range query by doing something, whatever. then you can do it, but that's not required by the assignment. Okay. For example, there are optimizations of dbScan where they use approximated nearest neighbors, which is something that's nowadays very, very common. Like there are libraries out there that do approximate nearest neighbors very fast. So they will enhance the algorithm a lot, but of course they will also make it approximate, right? Because then it's not exact anymore, it's not perfect anymore, and that may the let's say the impact of that, or the magnitude of the impact, is, who knows, depends on how good is the approximate nearest neighbor method that you're using. But that's something that exists, it's out there, and it's actually pretty simple to just import and use. But again, that's not required, and the required part is that you do it from scratch, right? So you should not use any kind of external library for doing that. So you really go and like calculate the distance between all points, and then you go through them and find the nearest ones. Okay, and that should be squared. The optimization is well, let's say the complexity is n squared, so that it's relatively slow. Lisa, please go on.
I just wanted to ask, what if we have maybe it's too early for this question, but I don't know, if I have a network, let's say, I have neighbors, right? I have nodes, I have edges. What do I take for radius? Do I take some length path?
Yeah, that's a problem. Because I mean, using this algorithm with networks, first of all, I have to be completely honest, I've never seen dbScan being used with networks. So in theory, it could be used, because as long as you have a distance function, it doesn't matter, right? So that would be interesting as an experiment. I don't know, maybe if you look for some papers, maybe there are some papers out there that have done it. But I would say that will depend on the distance function that you're using. So do you intend to use shortest path?
Let's say yes.
Let's say you're using shortest path, then you have to set up a radius like 1 or 2 or 3 or something like this.
Yeah.
For example, if you set a path of 1 or a threshold of 1, then you're just considering the immediate neighbors in the network, and that would, I mean, with a network, I can see here that maybe this is like, if you do it with a radius of 1, then that simplifies everything, because you don't even have to compute any kind of a path, because you have them already. But I would assume that would somehow break the algorithm, because that would be too simple, I think.
Yeah.
I don't know. So I would say, yeah, you set up a radius like 2, 3, 4, something like this, and I have no idea what's going to happen with that. But that should be interesting, because then you have these minimum points also that would limit the density. And I don't know, I mean, it's hard to say what's going to happen. It might be interesting to test, I guess. Might be interesting.
Okay, thank you.
And maybe you can take a look at, somebody for sure have done that before. So yeah, but then the algorithm, I guess, would be the same. Shouldn't change. I mean, probably should change if you want to optimize it specifically for networks, but not if you don't. So yeah, so this is what you have to implement. And again, like we discussed before, you don't have to. You don't have. I don't care which language you use. I don't care. Basically, you can do it in any way you want, as long as you submit a nice package that I can just run, right? So think about it before you submit it. Think about, okay, is this thing like compiled for Windows or something, or does it just works on Linux or something like this? If that's the case, we need to talk, okay? Because I'm on OS X and it needs to run on OS X somehow. So for example, if it's Python, that will be no problem. If it's any other kind of interpreted language that I can just very easily install some interpreter in some environment, and that's it, great. If it's a compiled language, that should also not be a huge problem, as long as compiling it is easy. And by easy, I mean just something that I can just do in a few minutes. If I need to install a whole development environment just to compile your code, that will be a problem. So please, if you're doing this in some kind of a weird, different like development environment and programming language, let's talk as soon as possible so that we can get everything sorted out, right? So think about how platform independent your code is, how easy it is to run it just anywhere. Okay.
Can I ask about environment?
Yeah.
Is it possible to implement in .NET, for example? So I just would provide you instructions. It shouldn't take a lot of time to run. Just install the SDK and make a .NET run.
.NET?
Yeah.
Can I compile that on OS X? I have no idea.
Yes, for sure. There is a .NET Core. It's a cross-platform.
Sure. So if you provide me with the instructions, I never did this before. So if you provide me with the instructions on how to install it and everything, actually, if you want to do it earlier, like if you want to send me an email or a message where you say, okay, this is what you have to do in order to get the SDK working, that's probably better, even better. And then I can just set it up once and then run all your code from then on.
Okay. But first, I would like to try in Python because I had some experience. And if it won't work, I think I'll just can write the implementation, but it will be much easier for me.
Okay. As long as I don't, what I don't want to do, if possible, is like install a new interactive, like an IDE where I have to open it. And I think I would very, very much prefer if it's just like command line.
No, there is no such requirement. It's just a command line tool called actually .NET, and there are two commands, .NET
All right,
and .NET Run.
That works much better then.
Maybe I could actually provide a shell script.
Yeah, if that works, that would be even better, I guess. But I guess I have to at least install the SDK, right?
Yeah, that's for sure.
Yeah. So please provide a command line shell or shell script or something like this. That would be awesome.
Okay, I'll text you in advance if I unable.
If you want to send me like a small test run, like you should do this, and then this thing should run, and then we test it, and that would be, I think, ideal.
Okay, I'll try.
Yeah. So then for now we're only considering Euclidean data sets. So I mean, Lisa wants to use networks. Of course, that she's very welcome to do that. But as a requirement, you need to deal with Euclidean data sets with arbitrary number of points and dimensionality. So basically, it's just a CSV file with many rows and many columns. I will not test it with like 10,000 rows because I know that's gonna take a while. It's a quadratic algorithm. So just think about something in around like a couple of thousand points, okay, maximum. Because really, we're not really talking about scalability here. So use the CSV format. Make sure that your program, whatever you do, accepts a CSV file as input, and that CSV will have rows and columns where the rows are the data points and the columns are the features, as usual, right? As the most common format for input. Then you have two parameters, which is, well, the epsilon, the radius of neighborhood, and then the minimum number of neighbors, the density threshold. And these, again, should be easy to set. I'm not really forcing you guys to do anything specific here, but I expect something like running a command line and then just giving a parameter like epsilon equals 5 and minimum points equals whatever, and then just run it, and that's it. So ideally, a command line program where I just put the parameters and that's it. if that is not the case, if you say I don't know how to do that, or I've tried doing that and I couldn't find a way, so I did it this way or that way, then again, give me instructions. Like for example, let's say you're running this in a Jupyter notebook because it's easier and you're doing that, and it's okay as long as the parameters are isolated from the code, like at the top of the notebook, for example. Then you say, okay, run this notebook, then the first cell you have to set the epsilon and the minimum points, for example, very easily. So I don't have to spend a lot of time like reading your code in order to understand where I should be putting the epsilon or the parameter. So as long as like, okay, it's in the first cell of the notebook, you just put there epsilon and number of points, and then you run the whole notebook, and that's it, you have the answer. That's fine, because that's easy. So as long as you send me those instructions very clearly, no problem. What I don't want is to take it, whatever you send me and just start guessing things around, because then I may guess it wrong. I will waste a lot of time correcting every exercise, and that won't be good for anyone. Then output. The contents of each of the obtained clusters, well, the contents of each of obtained clusters, there is no need to output noise points. So I just consider that whatever is not in the clusters is noise, so no problem. You will refer to data points by their row number, so like 0, 1, 2, 3, so on. So the first row point is data point 0, the second row point is data point 1, so on. So these are the IDs of your point. And then by default, you should write the results to the console. Again, if you're doing a command line thing, right? If it's a Jupyter notebook, it's also okay, it's an output, but just make sure that's like, okay, this cell is the output, so this is where you should look at, or something like this. Just consider I'm stupid. Consider I'm the most stupid person in the world, and you're giving it to me. So you have to explain everything, exactly what is supposed to happen, and where I should look, and where I should what's happening, everything. So consider like you're talking to a 5-year-old child. Explain like I'm 5. So each cluster's points should be in parentheses, separated by commas in ascending order. So for example, this is the first cluster. The first cluster has points 0, 5, 9, and 11. They are in ascending order, separated by commas, right? Then you do a space here, and you start the next cluster. So the next cluster has the points 1, 2, 8, and they are also in ascending order. Okay, close the cluster, the parentheses, space, one more cluster, 3 and 6. Finish the clusters. This is for 12 points and 3 clusters. This is an example of an output, and you can see that there are many points missing here. Like 4 is not here, 7 is not here because they're noise, so they were left out. Oh yeah, and the clusters themselves should also be ordered, so by their first element. So for example, the first element here is 0, here it's 1, and here it's 3. So that's how they are ordered. The rest of the points doesn't matter, as long as the first ones are, well, as long as the clusters are ordered by the first ones, okay? And basically that's it, just like basic DB scan, run it with a CSV, give me the output. If you want, you can give me some kind of a graphical output, but just remember that there is no one final way of showing clusters in a graphical output, especially when you have high dimensional input. The examples that I have given here, so these are 3 data sets, right? They're over here, these CSVs. You should be able to just, open them and use them as example. Let me see if I can show them to you. Yeah, well, I mean, it doesn't matter actually. It's the simplest possible kind of CSV. There's nothing else but data points in rows and columns. There's no like name. There are no names for columns, so don't put names in the columns. Don't put names in the rows. Don't add like don't expect actually to receive a column with point IDs or anything like that. It's just data in rows and columns, period. Okay, the very simplest possible type of CSV. And And then you have these 3 data points. They're all 2D, right? That's why you can visualize them like this. And I did it on purpose, of course, because I wanted you guys to visualize them like this and to have an idea of what's going to come out of the clustering method. Because or else I wouldn't have a nice way to visualize them. So I decided it was better to do it like this. One thing that you could do if you wanted, and you have a high dimensional input and you want to visualize them, is to do some kind of a projection, some kind of dimensionality reduction. We haven't seen that yet, but if you want to adventure yourself into doing that in order to generate a graphical output, that's okay, but that's not required, okay? Don't worry about that. This is only really just for testing. And these are the parameters that I used for these 3 data sets: 0.2, epsilon, and minimum points equals 20, right? So if you run these guys here in your algorithm with these 2 parameters, you should see something like this. If you don't, well, you know, maybe the colors will be different depending on how you draw them. So if you don't see this, then probably you should come next Wednesday in the tutoring and we should try to find out why. All right. But it should be something like this, at least. I'm not saying that every little point here must be exactly the same, although it should. I don't see why. I keep thinking about why, but I'm not sure exactly why it wouldn't. But I also don't want to say that I'm absolutely 100% sure that it would. So as long as it's slight, if there's some small difference, then we can try to think about why. But I would expect that at least it looks roughly the same. I just don't want to be like that to say, okay, I'm absolutely sure it should be the same. So yeah. Yeah, and this is the weekly exercise. I don't know if there is. Okay, Artemis, you want to ask a question? Please go ahead. My internet connection is unstable, it says here. Sorry guys for that. Not sure.
Sorry,
why.
Can you repeat that, please?
Yeah, I'm not sure what's happening with my connection because I'm using the cables. So the cable should be really good. But Artemis wants to ask a question, so please do it.
Yeah, sorry, just as a summary, because I didn't check exactly the file that you sent for assignment. So first we should check the DB-scan algorithms with the dataset that you put for assignment, and later we should test it on our datasets, or finally, I mean, the final assignment should come with the datasets that you put.
The submission is only the code and the instructions to run it. I will run it with some other data sets in order to test whether it is generalizable, let's say. These data sets are just for you, for you to test your implementation. Like, okay, this is more or less how it should look for these 3 data sets. Then you test it. But of course, the implementation should be general enough, because when you submit this to me, I will test it with other data sets.
Yeah.
And then I will see if it makes sense. But if you test with these data sets and it looks the same, then probably it's correct. You know. So, but the actual data sets, you don't need to send the data sets to me, because I will test it with other data sets. All right.
Yeah, thank you.
Okay. Yeah, and yeah, so I guess it's more or less it for this one. And then so here's the algorithm. You can take a look at that. This paper is really nice. This is like a discussion that people had. So DB-scan was published like many years ago, and then some guys published another paper saying that DB-scan was actually not that good and criticizing it. And then these guys published another paper criticizing the criticism and saying that, yeah, actually DB-scan is still very good, and so on. So this is kind of like a very nice academic debate, but I think nowadays it's still considered as being very good. And as you can see, for example, in this part here, this is interesting because they discuss improvements to the classic DB scan that's theoretically work better, like optics and LSDBC and HDB scan and star and all that kind of stuff. So there's quite a few different improvements that people did over the decades on the DB scan. Although, I mean, the core is more or less the same still. It's a nice, interesting paper to read. So yeah, okay, weekly assignment, that was it. Now project requirements. The project requirements are much more loose, or how do you say that? Looser? I don't say loser because that sounds stupid. But it's much more open and much more abstract. So we don't really have, you're not going to submit anything right now. This is just one step of the requirements that we are going to add to our your framework as you go through the course, right? And you will see later that like the first few ones will require a lot of stuff, let's say because we're starting from the basics, and then at some point it will slow down a little bit because then the basic stuff is already implemented, so you're going to reuse the basic stuff that came before, right? So then it's actually less things to implement. For example, data sets, distance measures, these are things that are going to be reused by pretty much everything in the course. So as after you implement it once, then you don't have to implement it anymore, of course. So yeah, a little bit of introduction here about clustering techniques. They are obviously very different from each other, but they also have some common things that you could think about, like when you think about clustering, right? So they take structured data as input. In this case, again, I'm considering only Euclidean data for now, but you will see that later we will twist it a little bit in order to make sure that actually it works with non-Euclidean data also. But they take some kind of unstructured data as input. Then they can usually be customized with different hyperparameters, right? So usually you have a clustering technique and that can be customized usually. Very few clustering algorithms out there that you don't customize at all. And then the output is some description of the extracted clusters. If you think of this as this kind of like a black box model of clustering, then you will see that by far most clustering techniques can be fit into this black box model. And then the inside working of the black box is abstracted away from you, but the black box is mostly the same. In addition to that, most but not all will use distance measures to compare pairs of points. So again, some clustering techniques will require the actual vectors because they need to do something with the actual vectors. Like k-means usually requires that, especially if you want to use centroid linkage. If you want to use centroid linkage, then you need to have the vectors. But if you're not using centroid linkage, if you're using like single linkage or something, then it doesn't matter because all that you need is a distance measure. So most of them can use different distance measures, and also there are some validation measures that are independent and external, which is something that I have still not discussed with you, which is the extra set of slides. So these things are kind of like common things to clustering, and these are the things that we want to model in our framework. Quick question from Christian. Can the dataset component be a wrapper of Pandas data frame, or we need to implement it by scratch? In the framework, in your framework, you can wrap everything you want. So the only place where you have to implement things from scratch is in the weekly assignment. But in the framework, all I want you guys to do is to build this skeleton, and then you wrap whatever you want inside that. So wrap Pandas data frame if you're using Python, or if you're using MATLAB, wrap whatever you want from MATLAB. Or I don't know how to do this in MATLAB, to be honest. So if you are doing this in MATLAB and you're confused, then let's discuss that. So in the week assignment, we need to read from CSV by hand. Well, I think exceptions will have to be made, but No, you don't need to read CSV by hand. You need to implement the algorithm by hand. So everything that's related to the algorithm should be implemented by hand, but not reading the CSV. No, you can read the CSV using pandas, yeah. But then, I mean, as soon as the CSV read, as soon as you have the data frame, or like, I would even say that maybe like NumPy's load text function is even easier. But as soon as you have the data frame, then everything that is done like by the algorithm itself should be done by hand, okay? But not reading the CSV, that would be outside of the scope of the course. Yeah, so again, yeah, so then the requirements here is like 4 components, right? One for a data set. And I mean this in a very simple way, like really, you don't need to do it in a very complicated way. If new requirements come up, then you can expand it. But a data set is just basically a way that you can say, get the data points. Like, for example, data point 0, data point 1, 2, something like this. The reason why I want you guys to abstract this is because later we're going to use non-Euclidean data sets. And then we need to think about a data set in a way that's not necessarily Euclidean data sets. It's just a set of data points. And you're taking the data points from that. And then I say the features, but the features in this case are only for the Euclidean ones. And later we will adapt it a little bit so that maybe it has features, maybe not. But for now, it does have features. So somehow you want to have, okay, give me column 1, give me column 2, or give me column 3, and so on and so forth. So as you can see, it's very much like a data frame, but simpler. Then you create a component for a distance measure, some distance measure. Okay, give me 2 points, get a value out of that. And some distance measures can be parameterized also, as you will see later, but most will not. So it's basically just a function that you say, okay, compute the distance measure for these 2 guys. Okay, here it is, that's it, right? And then you implement some different ones. Create a component for a clustering technique, following more or less the black box that we discussed. So you should accept as input a data set. And by data set, I mean this guy here, right? So this is the input that you should take, like this abstraction of a data set. And optional hyperparameters. And the hyperparameters, of course, must not be hard-coded. So it's what I mean here is like the names of the hyperparameters, not the values themselves, but the names should not be hard-coded because, for example, dbScan will have epsilon and minimum of points. And then k-means will have k. Hierarchical clustering will have linkage, type of linkage, and so on, right? So it's just that what you have to say is, okay, a clustering technique has hyperparameters. Which are these hyperparameters? Well, it depends on each technique. And then one parameter should be a distance measure, unless, well, just assume that it uses a distance measure. There are very few clustering techniques that will not use distance measures. So just assume that they use distance measures, and then just add there, okay, you need to set up a distance measure somehow. The output, I will not, I thought about that. I don't know exactly how we can abstract away the output. So I will just kind of leave it to you to define your own format for the output that you want. One way would be like a list of lists. So a list of data points, depending on your language. In Python, for example, so every list is a cluster, and then you have a list of lists, which is all the clusters. That could be, I mean, I don't see really how we could have this in a very standardized way. So just do what you think you should. Maybe you can create some class here called clustering output or something, if you think it makes sense. And then you create a component for a quality measure for clustering. This is what we're going to see now in a few minutes, hopefully. But basically, it's just a quality measure for a clustering. So it should take as input the results of the clustering technique and the data set, because usually, in order to compute the quality measure, you need the results, but you also need to compare the results with the full data set because you need to check some stuff usually. So then you take these two things and then you output some value, like this is the quality, 0.85 or whatever. Some clustering, some quality measures will also require labels, because they will check the clusters against the labels. So I didn't put it here, but maybe it might be an interesting idea to have here in the data set to have an extra like attribute for labels, the labels of the data set. And then when you send the data set into the quality measure, since the data set is part of the input, then the data set carries it with itself its own labels, and then you can just take them and use them. So I didn't really think it through here. I should have maybe said that it should expose methods to get the data points, the features, and optionally the labels. So maybe I can just add that later here because it makes sense. And then finally, notes. Remember to write also at least 3 different implementations for each component. So I will not be actually checking this specifically right now. Like, you're not going to submit this now, right? But at the end, when we discuss the framework, this is how we're going to evaluate to consider whether your framework is actually working or not, and as it should. These benchmarks, right? The ability to build a pipeline in order to do a benchmark of a technique, for example. So you should write at least 3 different implementations for each component. And again, as per Christian's question, when I mean write, I don't mean that you have to write from scratch, because that's not the point here. All the implementations can be simply wrappers around anything else, as long as the skeleton was made by you, and that the skeleton allows you to run these kinds of pipelines in order to do benchmark. So for example, let's say I have 3 different data sets, right? Whatever, like these 3 data sets that I sent you for the weekly assignment. Then you have 3 different distance measures, 3 different clustering techniques, and then you build a pipeline such that for each data set, you run each clustering technique. And for each of these combinations of data set with clustering, you try each of the distance measures. So it's like 3 times 3 times 3, that's 27 different runs, right? And then well, actually, I forgot here to say, so like 3 different implemented techniques, 3 different data sets, 2 different quality measures. Okay, I forgot about the 3 different distance measures. So actually, in the end, if you have 3 of each and you really run a pipeline with every possibility, then you will have 27 times 3, which is 81. So you would have actually 81 runs here if you had these 3 different implementations for each of them. And then just make sure that it works, because this is the kind of thing that we will evaluate in the end. So if that works, then you're fine. By different, so a question from Christian, by different implementation, do you mean different data sets, for example, or different components? I mean 3 different implementations for each component. In the case of the data set, maybe we can be flexible with that, because I'm not sure. We will have actually 3 different implementations for data sets, at least we will see 3 different types of data sets in this course. So you could have 3 different implementations of data sets. But I also mean, in this case, I meant like three data sets. So that they are not really 3 implementations of data sets in this case. But in the case of the distance measure, the clustering technique, and the quality measure, then they are actually 3 different implementations of the components. But in the data set, I understand that it's a bit ambiguous. So, I mean, you could have 3 different data sets, or you could have 3 different types of data sets, right? So for the data set, it's not really that big of a deal, I guess. But we will see 3 different types of data sets at least. Actually 4, as long as I remember. So it's just a normal Euclidean, then text, networks, and streams. So at least these 4 different types of data sets we will go through in the course. So they could be at least 4 different implementations of the components of a data set. Okay. Now, even though streaming might be a challenge, so maybe if you have to drop one, drop streaming, because that would be hard. So so yeah, but basically that's it. This is again very like open and loose requirements, and because I really want you guys to just exercise your creativity and do it in a way that makes sense to you with your programming language. And but the idea here is that you learn the abstractions. You learn that the whole thing is basically a set of abstractions, and then we understand this difference between the black box and what's inside the black box. Okay. Kumar, a question from Kumar. 3 distance measures like normalized Euclidean distance, don't understand what could be third, maybe minimum in any dimensions or so on. Yeah. There are many types of other distance measures that we're going to see, and even especially when you're considering different types of data. So for example, for networks, you have different distance measures. For text, you have different distance measures. And okay, I will take a second because I understand that my connection is not good. So I will pause and start again. Yes, 3 different distance measures. Euclidean distance, normalized Euclidean distance, squared Euclidean distance, and all other kinds of generalized Euclidean distance that you have by using different powers, you know, because the normal Euclidean distance is the second. So, but you have also the other types. I won't get into details on that right now because we're going to talk very much about different distance measures as we go. But there's also different distance measures for different data sets, like for networks, for streams, for text, and so on. They also have their own distance measures that should be implemented with in the same framework. So then, but there are some others as we will see later. But there, so just think of just be prepared for them.